All right, we are now in video 4 of the second derivative test. Let's read example 3 and see how we can use what we know for this situation. Let g and h be twice differentiable functions. So I can take the derivative of each of those functions twice and know that the derivative exists. With g prime of x equals h of x times x minus 2. The graph of h, the original function h, lies below the x-axis for all real numbers of x. Does the graph of g have a relative minimum, a relative maximum, or neither at x equals 2? And then can you give a reason for your answer? So this is a very focused question in that they're asking me about a very specific point, and that is at x equals 2, right? So let's figure out, what do we need to know? Well, we need to know, do we have a critical point? Is x equals 2 even a critical point? Well, what do we get when we plug 2 into the derivative of g? Because remember, this is about g, the graph of g. All right, so let's plug in 2 into the formula, and we're going to get h of 2 times 2 minus 2, which is going to be h of 2 times 0, and that is 0. So x equals 2 is a critical point. It's a critical value because when I substitute that number into the first derivative, I get 0, right? It makes the first derivative of g equal to 0. Great. Now let's check it into the second derivative. But to check it into the second derivative, we need to take the derivative of g prime. The derivative of this, I'm multiplying, so I've got to do a product rule. Take the derivative of the first times the second, plus take the derivative of the second times the first. And now we're going to substitute 2 into the second derivative. So that would be h prime of 2 times 2 minus 2. Oh, that's going to be 0, and that's going to cancel that out. Plus 1 times h prime is just h prime of 2. Wait, I think I put an extra prime here. I sure did. I don't need this prime. Remember, it's a derivative of the second times the first. The derivative of the second times the first function. The first function is h of x. So really, I'm just evaluating h of 2 because this is going to become 0. And h of 2, they told me that the graph of h lies below the x-axis. That means h of 2 is less than 0. It's a negative value. If the whole graph is under the x-axis, then all my y values, my output values, my graph values are negative. So therefore, I know that the second derivative of g is negative. Therefore, I know it's concave down, and I have a relative maximum. By the second derivative test, since g prime of 2 is equal to 0 and g double prime of 2 is less than 0, there is a relative maximum of g at x equals 2. I checked to see if I had a critical value. I did. And then I checked that critical value into the second derivative to determine the concavity, because if it's concave up, I'm going to have a relative minimum. If it's concave down, I'm going to have a relative maximum. It turned out to be negative, so it's concave down. That's how I knew that it was a relative maximum. But that only works if I know that the point that I'm checking is a critical value, if the first derivative is equal to 0. We're going to do example 4, and then we're going to pause this video. Example 4 says we have a function. It's continuous for all real numbers of x. The table above includes information about f prime of x and f double prime of x for selected values and intervals of x. So not all values are given here. That's important to remember. Part A, for each of x equals negative 5 and x equals negative 2, determine if the graph of f has a local minimum, local maximum, or neither, and explain your reasoning. Okay. Let's start writing out the sentence. Since f prime of negative 5, what does f prime of negative 5 equal? F prime of negative 5 is equal to 0. So I have a critical point at negative 5. And f double prime at negative 5, what is the second derivative value at negative 5? It's negative 2. That's less than 0. That means it's negative. If the second derivative is negative, that means it's concave down. And if it's concave down, by the second derivative test, f has a local maximum at x equals negative 5. That's the best I can do. They never gave me information about the original function to find the y value. What is the local maximum? I don't know what the y value is. But I know that at x equals negative 5, that local maximum exists. Okay, can I do the same thing again? Since f prime of negative 2 equals, what is the derivative value at negative 2? Equals 0, yeah. And f double prime of negative 2, what does that equal? It equals 0. The second derivative test is inconclusive. However, there's something else we do know. So I can't use the second derivative test like I did at x equals negative 5. But what I can do is go back to the first derivative test, because if you take a look, the first derivative test changes from negative values to positive values, from negative values to positive slopes, from negative slopes to positive slopes. That means there's a relative minimum. However, since f prime changes from negative to positive by the first derivative test, there is a local minimum at x equals negative 2. Haha. So the second derivative test is inconclusive. However, I can go back because this is a table of values and I have signs from negative 5 to negative 2 and from negative 2 to positive 3. So I know what happens exactly at either side of negative 2. The derivative goes from negative to positive. That means my slopes go from negative to positive and I have a relative minimum there. Haha. Yes. Okay. Let's keep going. Can you find and classify any additional known values of x where f prime has a relative extrema? Yes. Where does f prime have an extrema? Well, where is f prime equal to 0 or undefined? Well, we already checked this one. We already checked this one. If I look here, this is a critical point because the first derivative does not exist. However, I don't know what happens on either side. So it could be a relative extrema, or maybe it's just nothing. I don't know. So I keep on looking. At 0. So then I can say, since f prime at 13, that's equal to 0. The derivative is equal to 0. That's a critical point. And f double prime of 13 is 1, and that's greater than 0. That means I have concave up parts. By the second derivative test, f has a relative, or in this case, no, they use the word relative. So they have a relative, let's see, if this is concave up, then I have a relative minimum at x equals 13. Yes, it worked. So notice here's a situation where the function is not given to me in terms of an equation. So I can't just take the derivative and take the derivative again, but I have some values of the first and second derivative, and in this case, enough values to do some analysis. All right, next part. At which values of x must the graph of f have a point of inflection? So when do points of inflection happen? When the second derivative changes signs. It doesn't matter if it changes from positive to negative or if the second derivative changes from negative to positive. Whenever f double prime changes signs, then I have that. Okay, so where does the second derivative change signs? Here's negative, it's negative, it's negative, it's zero, it's positive. Ooh, here, it changed from negative to positive. I'm going to keep going. Positive does not exist. Negative, ooh, is that one? And then I'm going to keep going. Negative, zero, positive. Ooh, is that one? What do I do? Do I have enough information to show me that it does exist? I think this one I do. And I'll tell you why. Because all I'm looking is for the derivative to exist. I mean, for the second derivative to change signs. Well, it changes from positive to negative on either side of 3. However, be careful. When I come over here, I see negative, but then I see positive. But this is not on either side of 11. Specifically, I don't know what happens at 12. Right? Like there's missing information here. All the other ones, the intervals have been right up to the critical point, right up to the critical point. But over here, I go up to 11, and then it skips to 13, and then it skips to 14. It's not like a continuous interval, so I can't really tell. So I think F. Oh, let me do it in the color that I did it. F has points of inflection at x equals negative 2 and x equals 3 because f double prime changes signs. The second derivative changing signs guarantees me on either side of the point, right? Guarantees me that that point is a point of inflection. Okay, I'm going to let that digest a little bit. If you want to pause the video to kind of soak everything into your brain, you can. But I'm going to do the last part, which is going to take us into another way to tell whether I have overestimates and underestimates. Or a way to tell, I should say. Number 4. The line tangent to the graph of f of x at x equals 6 is used to approximate f of 10. Will this approximation be an overestimate or an underestimate of f of 10? So remember, we talked about how we can do linear approximations if I have a graph, and I don't know, we'll just do like a graph there. And if I have this is 6, and then this is 10. So if I'm looking for the point on the graph, I could draw a tangent line, and the point on the line at 10 is a pretty good approximation for the point on the curve. Well, maybe not in the graph that I did, but they're saying that the approximation at 10 can be approximated, or the value at 10 can be approximated with the tangent line at 6, right? But this is the idea that they're pretty close to each other. We can approximate one for the other. But the question is, how do I know if it's an overestimate or underestimate? Well, if you go check at x equals 6, let's go to the table. At x equals 6, that would be in this window. My second derivative is negative. Okay, so this is what I'm going to say. Since f double prime of 6 is less than 0, that means I have a concave down situation. If I have a concave down, when I draw that tangent line is going to be above the curve, so it's going to be an overestimate. So we can use concavity to figure out whether my approximations using tangent lines are overestimate if it's concave down, or underestimate, like this one, if the graph is concave up. So the second derivative being negative tells me that it's concave down. Since that's true, then f of 10 will be, maybe I should say the approximation for f of 10. Then the approximation for f of 10 will be an overestimate. And the table at the bottom of this page explains that idea, right? If I have if I have a concave down situation, when I draw the tangent line, it's going to be above the curve. So any estimate that I use with this line is going to be an overestimate. But if my graph is concave up, then the tangent line is going to be under it. And so therefore, I'm going to have an underestimate. So just a tip here, it says explaining why a tangent line is over and under, but be sure to state that f of x is concave up or down over an interval and not just at a point. Okay, so maybe we should say, since f double prime is less than 0 because f double prime is less than 0 on, what was the whole 3 to 11, then the approximation for f of 10 will be an overestimate. And that would give you the points that you need for that particular problem. All right, we're going to pause this video. We'll come back one last time for a fifth video using the second derivative test. And this time, we're going to investigate some implicit equations.